So let's walk through an example of an ANCOVA, specifically what we're looking for in SPSS and kind of how to conceptualize this. So in this example, is there a difference in attitude towards GLBTQ populations after safe zone training, after accounting for existing knowledge about the GLBTQ population? So the idea here is that if someone already knows about all this information, does the training really have an effect? And is that effect worth measuring out? So the idea here is that if we're measuring knowledge and attitudes, that probably previous knowledge already has an effect on that DV. So by measuring previous knowledge, we're not expecting that previous knowledge is going to impact whether or not you got the training, but we are expecting it to be related to our outcome, your attitudes. So that's perfect for an example of something we might want to measure as a covariate. So again, we always want to ask ourselves, is the covariate something that we'd expect to be related to the DV, but would not be expecting it to be related to the IV? So our dependent variable here is attitudes, covariate is existing knowledge, and the independent variable is training or no training. So is there a difference in the difference between those with and without training? Does the same relationships exist after accounting for the variance shared by the IV and the covariate? And again, on the DV. So when the covariate is continuous, an ANCOVA is computed by comparing a regression equation that measures the relationship between the covariate and the outcome variable. So again, what we're looking at is we're comparing the predictability of outcome scores. So again, our null hypothesis is basically that there is no real effect, and our alternative hypothesis is that using separate regressions predict equations for each factor level. In other words, the covariate does have some impact. So our null hypothesis is that our covariate predicts attitudes from existing knowledge, and our alternative hypothesis is that it predicts attitudes from existing knowledge for those in safe zone training and for those who do not have the training. In other words, our null hypothesis is we're expecting a relationship, but our alternative hypothesis is that that relationship actually is going to make the hypothesized relationship between our actual IV and our DV stronger or more noticeable. So let's walk through that example, looking at what we're going to see. So does the differential treatment of learning disabled children affect reading scores after adjusting for differences in child's previous reading ability? So I'm shifting examples, but it's basically the same idea here. So again, differential treatment, that is our IV. So we're using different interventions. We're looking at a population of learning disabled children, and our DV is their reading scores. But what we're wanting to adjust for is, again, the children's prior reading ability. So we're wanting to look at something that we'd expect to be related to the outcome, reading scores, but would not be related to whether or not they were getting treatment. So our IV is type of treatment. Our covariate is the pretested scores on reading subtests of the wide range achievement test. And our DV is post-test scores on that same test. So again, we run our analysis and we get our output of our ANOVA. And in here we again have our corrected model, our intercept, we have the treatment effect, we have the error effect, and we have total. So again, our treatment effect, we find that it is not quite significant 0.06, partial eta squared of 0.6, an F of 4.52. And there's our error. So again, we can see where our mean squares are coming from. We see our sums of squares. So example in treatment, sums of squares is 432.889. We divide that by 2. That gives us our mean squares of 216.444. Again, our sums of squares of error is 287.333. Our degrees of freedom is 6, so that number divided by 6 is 47.889. And again, our F of 4.52 is simply that 216.444 divided by that 47.889. If we add the covariate, now we actually have that pretest value. What we're looking to see is, by putting that pretest in, does that change what we actually find? So again, we look at that treatment effect first, and we find actually it is now significant at 0.045 with the partial eta of 0.71. In other words, by using the pretest to remove that variance from our outcome variable, we're actually creating a situation where now it's a stronger relationship when we just look at treatment's effect. And again, we see that error there has now been reduced. So though treatment is also smaller than it was before, it's been slightly reduced, which means that pretest did have some relationship, probably minor with treatment, it was a much stronger relationship with the actual, again, outcome or unexplained variance, the error variance. And that's kind of what we're looking for. So not every covariate is going to work. In fact, sometimes when we put a covariate into an ANOVA, we're actually going to find that it worsens the effect. That's going to be a covariate which is probably related equally or maybe even more so with the IV than the DV. And that's one of the reasons we want to theoretically ask ourselves, do we expect it to be related to the DV and not expect it to be related to the IV? Because that's the situation where it's going to make a more clear picture and allow us to find a meaningful effect easier. And again, we're looking at that pretest. Now notice that pretest isn't actually significant, 0.08. It doesn't necessarily have to be significant because we don't have a hypothesis about it. We simply are saying that we think it is related to our DV and therefore it's noise that we want to remove. So the assumptions of the ANCOVA, the outcome should be normally distributed within groups. Variance between groups should be homogeneous. Observations between participants should be independent, assuming a between-subject design. And the relationship between the covariate and the DV needs to be linear. So again, we have the standard assumptions of ANOVA, normal distributions within groups. The variance should be homogeneous, so we shouldn't see different types of variance in different groups. The observation should be independent if it's a between-subject design. The main difference here is we do need to make sure the covariate and the dependent have a linear relationship. That is an assumption of the ANCOVA. Because again, it is simply looking for linear relationships. We're not making an adjustment as we would in multiple regression to look for nonlinear. So if there's a nonlinear relationship, it's not really going to help our analysis.